All right, so we actually have one more example for polar coordinates, and this one is computing a volume, right? So let's say we have a region which is bounded above by a paraboloid, z equals 4 minus x squared minus y squared, below by the the xy plane, and inside the cylinder given by x squared plus y squared equals 2y. Right? It's a little challenging to sketch that 3D region, but the cylinder here is just a little off-center up on the y-axis. And then you have the dome coming down over it. So it's like a roof that slopes down. Right? But let's not worry too much about visualizing that because the problem sets it up pretty well. All right. So, well, the first thing we should do here is put all of these things in polar coordinates. So z equals 4 minus x squared minus y squared. Well, that z equals 4 minus r squared, right? Because x squared plus y squared is r squared. The xy plane is still z equals 0. And what about the cylinder? So let's say A and B, the cylinder, x squared plus y squared equals 2y. Well, x squared plus y squared is still r squared, but 2y is 2r sine theta. Right? So one of these r's cancels with this guy, and we see that that cylinder is just r equals 2 sine theta. Okay? Right? You can imagine here we're kind of putting polar coordinates on the xy plane and letting z do its thing. That's if you want to visualize it like that. All right? So, well, now we need to set up an integral here. So, of course, the area, or sorry, the volume. So this is going to be given by integrating over the base the height of the region. Well, it starts, the sort of floor of the solid is the xy plane. The height is this paraboloid. So setting it up in Cartesian coordinates, we'd get something like this. Right? But this isn't going to work out so well in Cartesian because of this region here. Right? What that region is a circle of radius 1 centered at 1. So you're going to get something like this. It's not a very good circle, but we'll talk a little bit more about why it's that circle in a second. But, so this is going to be D, this thing here. Right? So, we'll worry about that in a second. But here, notice we just get 4 minus r squared. dA, we'll end up using r dr d theta again. But now, so this curve here, this is r is 2 sine theta. Right? It's not a very good writing of that. Let's clean that up a bit. All right. So we get r equals 2 sine theta. Right? But now we have to figure out bounds. Well, if we're doing r first, we can go ahead and set that up. Because remember, r starts here at the origin and then goes out. And if you notice, it always starts here at the origin and ends up hitting this curve 2 sine theta. So the r bounds will be 0 to 2 sine theta. But what about theta? What are the bounds on theta? Well, you can imagine this being sort of sketched out by starting here at 0 and then going around once and then coming back to 0. right? So really, we just need to find where this guy is 0, right? So r equals 2 sine theta equals 0. Well, that's the same as just asking when is sine theta equal to 0. Of course, that's at n pi. So we can just use 0, theta equals 0, and pi. Those are good places. Okay? So then the bound here goes from 0 to pi. And that's it. That's how you set up the integral. I'll let you check on your own, but this answer should be 10 pi. Unless my notes are wrong, but I think this is right. Okay, so hopefully that setup made sense here. And all I can say at this point is just practice, practice, practice. Do a bunch of these guys. Never, ever, ever forget about the r, polar coordinates. And see you next time.